Hello everybody, welcome to the course Phase Diagrams in Single Component and Binary Systems, and today we will try to introduce this course to you, and gradually we will go deeper into this particular subject matter. Now, whenever we try to understand these phase diagrams, we need to define phase diagrams. And phase diagrams can be defined as a kind of graphical representation of stability of different phases that can arise in a system as a function of system variables. Now, let us write down this particular definition. Okay. So, now this is a definition. Now, there are few terms like stability, different phases, system variables, and when we talk about system variables, here we are talking about pressure, which is denoted as P, temperature, which is denoted as T, capital T. Composition, interestingly, though the components composition means it has various components, then only we can measure in terms of mole fraction or weight fraction or atom fraction. So, that means there will be components, there will be components or constituents in a system or even in a phase that will be decided by the relative presence of those components. So, finally, we will see that actual variable will be, instead of composition, we will try to indicate the variable as chemical potential. We will take chemical potential as one of the important aspects while drawing phase diagrams, or rather in order to decide stability of a phase or a combination of phases in a system. So, these important aspects we will try to define in our next lecture, but today's lecture will try to understand that by giving an example in case of single component as well as binary case, and try to see what do we mean by those stability, as well as what do we mean by system variables. Now, if we look at a single component system like water, okay, we will try to learn why water, though it has hydrogen as well as oxygen, but still it is considered as single component. For the time being, you take it as a single component. Okay. So, water phase diagram so this is considered as a single component system, though there are two species, one is hydrogen, one is oxygen. We will learn later why it is considered a single component. Now, in this case, the schematically if we try to see the phase diagram, it has pressure on y axis, it has temperature on x axis, and the schematic look of the water phase diagram is like this. Okay. So, this is called triple point, this is triple point, and these lines are basically phase boundary lines, and here we have solid water, here we have liquid water, and here we have vapor. And we will see later on that what are those specific temperatures, pressures, all those points we will try to understand later. But I am just giving some idea about the stability of different phases in a system and what are the system variables. In this particular diagram, if you see carefully that we have taken pressure and temperature, these are the two variables which are system variables, and we have marked different zones as solid, liquid and vapor. So, if we try to look at this particular line, this line, so if I check this line is basically called solid liquid equilibrium line. So, this line is liquid vapor equilibrium line, and this one is solid vapor equilibrium line. And we'll learn in detail what do we mean by equilibrium. It's not a very easy term, though we loosely use it, but equilibrium needs to be understood correctly. So, in the next class we will try to learn all those definitions, but equilibrium actually gives you the stability part. Okay. For example, if I decide any point in this particular phase diagram, let us say I have chosen this particular point. Okay. So, this particular point I can mark its coordinate. This one is the pressure P1, let us say this one is the temperature, okay, T1. Now, T1 and P1, if I fix those two points, pressure and temperature, we mark it accordingly according to that point, that coordinate of that point. At that P1 as well as T1, we would get solid as a stable phase. We cannot experience liquid or vapor as a stable phase, but that does not mean that their existence, liquid as well as vapor existence, is not there. That could be there, but those could be in terms of a metastability. So, now we see another term that is coming up, which is called metastability. So, now stable as well as metastable, fine. So, these two terms are coming. So, if I try to understand what could be the stable and metastable, for that we can look into energy diagram like this. So, I can talk about this is energy axis, and this one could be reaction coordinate, and it can be also considered as distance. Okay. I can take it as a distance. Now, I can think of a kind of a rooftop, and I can take the base of that building as another energy level. So, this is the rooftop is one energy level and base is the another energy level, and let us say there is a kind of barrier which is the basically fencing of the roof. Okay. So, now if I try to look at, there are two balls, okay, which are labeled as E1 as well as E2. Now, if I could take this ball and take it to this level where we do not have any support, this ball easily can roll down, can fall down and then come to this place. Okay. And from there it will be stationed there. It will not have any movement from there. So, that means I can see that this particular position has a tendency to come to this particular part spontaneously. Okay. But that case we should not have this particular barrier. Okay. This is a barrier, okay, or the fencing. So, you can say this is barrier. Okay. Now, in order to get to this position, this particular ball has to be raised to this point, and then a little push, it will come to this level. Okay. So, now when we take this instance, I could see that E1, the ball at E1 has a kind of tendency to go to E2, and then it will be stand still, and in order to do that we have to lift it to this top of the barrier and then push it little bit. So, this particular diagram gives me the idea of metastability. So, if we try to look at E2, so E2 is the, as per this diagram, is the final position where the ball can rest, but energy levels higher than E2 that can have a chance to come to E2. So, that means E1, E2 could be considered as the most stable condition as per this particular diagram. So, then that will be considered as stable consideration, but energy level higher than that, we call all those levels as metastable levels. So, these levels will be considered as metastable levels. And we can also find out the hierarchy of metastability. So, you can say that this one would be the lowest metastability. As we go up, it will have higher and higher metastability. So, similar situation happens in this particular point. All the other phases like liquid and vapor, they could also have their existence, but their existence is far above the solid existence as per that P1 and T1. So, that case we will say that the solid water would have the most stable situation or condition in that particular zone and the solid zone. Okay. So, that way, and once we consider it to be a stable zone, I mark it as a stable phase that is existing there. Okay. Similarly, I can have liquid positions or vapor positions, and then accordingly I will get single phase, stable phase. But now if I try to mark on this particular line, so that mark would give us an idea that solid as well as liquid both are having the similar energy levels. So, both can coexist. Okay. But if we try to look at vapor, so vapor would have existence, but in terms of a metastable existence. So, though that means I could say that along that point, any point I choose, I will have liquid as well as solid water, they could coexist. Okay. And when they coexist, because they have the similar energy level, we talk about its equilibrium situation. The two phases are in equilibrium. Okay. And similarly, I will have all those points on single phase, on those lines, they could have a two phase equilibrium lines. And if we shift a little bit by changing the pressure and temperature, I will land up in single phase zone. For example, if I go this way, that means it will become liquid. So, if I look at this point as well as this point, so that means we have an entirely solid region and then it goes to liquid region, and during that process I am fixing the pressure, but I am changing the temperature, that means I am increasing the temperature, and that time I will get melting operation. Okay. It is called melting. So, solid going to liquid at a constant pressure, pressure constant, temperature increasing. So, I will get melting. But if I try to go back like this, that time I will get it, I will get solidification. So, this is one. Second part, if we try to look at this, so if I say liquid going to vapor, this is considered as, and remember I am fixing the pressure constant and temperature I am varying only the temperature. So, that time it is considered as vaporization, and if we go back we will call it condensation. Okay. Similarly, if I check this, I can see solid going to vapor at a constant pressure by increasing the temperature. This one would be called as sublimation, and if I reverse is vapor to solid at a constant pressure by decreasing temperature, that would be considered as deposition. Fine. So, I could see that if I have an understanding on the system variables, then I can change one of the system variables fixing another, and then we can get to one phase to another phase, and these are all called phase transformation. Okay. So, that means this is a kind of graphical representation of stability of different phases, and then once I know this, I can actually go a little ahead and try to understand how to change one phase to another. Okay. And we will try to also see examples of the effect of those phase transformations. You will see a great experiments can be performed to understand the effects, and they are fantastic actually. We will see that later. For example, in high altitude regions, the ice formation is a big problem while transporting water or taking water from one end to another through pipelines. And that time there is a possibility of pipeline breaking or failure of pipeline. So, why that failure happens, that would also be explained through this phase transformation. In fact, you might have taken we call it ice the ice creams, where you might have seen that the local vendors, they try to make the ice powdery ice, they take it, and then around a stick they press it very hard, and then they get a fantastic shape, a solid powder. From powder you get a solid object, a kind of shape, and that shape they put lot of sugar syrups and they make fantastic ice creams. So, how those powder particles they get assembled and joined together. So, that is also because of the magic of phase transformation, and that kind of information can also be, that kind of situation can also be explained using phase diagrams. Okay. So, that means you could see that the stability, now come back to this definition, stability of different phases in a system. So, this is water phase diagram, water system, I am talking about water system, okay, and it has different phases, those are marked and separated by boundaries, and those boundaries are basically two phase equilibrium boundaries. So, that means both the phases will coexist under stable condition. Okay. And the third phase, in case of single phase zone, the other two phases will have their existence, but in terms of metastable existence. But on the lines, all those boundary lines, two phases will be under stable equilibrium, they will have their stable existence, but the third phase will have metastable existence. So, like that we could explain all those aspects, and under the influence of what? Under the influence of system variables. Here we are taking pressure and temperature to be our system variables. And here the third variable, which is composition, does not come into picture. Why? Because it is a single component system. So, single component system, the composition does not have any meaning, all the time it is 100%. But once we go to multi-component system, starting with binary to binary to ternary to quaternary to quinary, all those systems like ternary is 3-component system, quaternary is 4-component system, quinary is 5-component system. As we increase the components, then we have to bring in composition factor, okay, because the relative presence of different components we have to take care, okay, we have to take into consideration in order to understand the stability of different phases. And in thermodynamics, this is a kind of beauty of thermodynamics. In order to understand a system, we try to fix one or two variables, so that it boils down to a function of one single variable. Okay. For example, if we see in this water system, simple 1-component system, when we try to understand these 6 phase transformations, we fixed a pressure. So, that means everything becomes temperature function. So, like that we could have fixed temperature, everything could have been pressure dependent. Like that way we make things easy, at the same time we can understand the system. Okay. So, now you see the importance of this, at least from this diagram, at least we could see different phase transformations. How the phase transformation happens, that is a different ball game altogether, we have to look at kinetics part of it. But phase diagram, when we try to learn, we will not learn kinetics part. Okay. Now, why kinetic part become very important? Because let us look at this diagram again. Okay. In this diagram, at least I could see from the position of the ball on the rooftop as well as at the base of the roof. Okay. So, where it becomes absolutely stable. So, we could see that the ball cannot by itself go to that stable positions. We have to give a push, and we have to increase the energy to topple that barrier. Okay. So, that toppling part, this particular energy part we have to supply, and then only the ball can go to the other end by free fall. Okay. So, this particular part which is the energy barrier, that comes under kinetic factors. Okay. So, what will be the rate at which the ball would move to the other end, and here I am talking about ball, it can be a particular reaction. So, one reaction, for example, in this case melting point, melting or solidification, whether the system would actually melt or solidify, that would be decided by the barrier I am providing to that phase transformations. That barrier consideration will come under kinetic factors. Okay. So, we will not consider that part, we will only talk about how to get this phase diagram, we will try to learn that, fine. So, now at least from this diagram we could see that I can absorb, I can sense that what is the stability of different phases, what is the condition for coexistence of different phases, and what are the phase transformation that I could achieve. In fact, in this particular diagram there is one point, one single point where all 3 phases can coexist. So, that point is here, which is called triple point, and the triple point I have solid, liquid as well as vapor, all can coexist, okay, and under stable conditions. So, that means that triple point is also a very important point. Now, what will be the conditions at the triple point or two phase points or two phase line. So, those conditions or the variables, what variables I should consider in order to get those points, that falls under a particular rule called phase rule. So, phase rule decides what will be the thermodynamic function that will be needed or that should be fixed to get to that point. Okay? And rather another way to put it up is what will be the equilibrium conditions to get to those points. So, the phase rule also we will try to learn when we go ahead, okay, and try to, the phase diagram will come in a later part of this particular lecture series, but this will be also a very important aspect. Now, at least from the single component system we could see different aspects of phase diagram. So, let us look at another diagram which is called binary phase diagram. So, binary phase diagram, let us take one simple binary phase diagram. Let us say copper, this is in case of binary phase diagram, we take this one as temperature and this one as composition. Composition can be marked as percentage of the element, here it is copper let us say, and here it is nickel. And in case of water system, remember I have not put any values. So, those values I will put later on, but this is a schematically this looks like this in case of water. Okay. But in case of copper, so this is 100% copper and this is 100% nickel, and in between I can put in terms of percentage of nickel or mole fraction of nickel. Mole fraction is considered as X nickel, like that way I can put it up. And here I have to fix one particular system variables. Here I am fixing pressure. P is fixed. Okay. So, when P is fixed, the diagram looks like this. This is a diagram, typically the diagram that forms, and here we have liquid, here we have solid, and since it is 100%, so here I am seeing that solid to liquid transformation happens. So, I can put this point as Tm copper and this one will be Tm nickel, that means the melting point of nickel as well as melting point of copper, and in between I have such I-separated diagram. And in order to understand, so these lines, any lines we are doing, so those lines, these lines will be all equilibrium lines between two phases. So, this line is called liquidus and this one is called solidus. Okay. So, this is, and now let us say if I take a line like this, let us say I have marked different points. Let us say I have marked 4 points. Let us see what are the phases. And here the system variables are what? Composition is one system variable and temperature is one system variable, and here I have put pressure to be a fixed condition. And when we take a vertical line with respect to composition, I am fixing the composition also. But you will see that this phase diagram will tell us, so what are the different phases that can come out as we go down from higher temperature to lower temperature. So, for example, at this one let us mark A, B, C, D. So, A point I have only liquid, and in this liquid I have copper as well as nickel of this composition. Let us say this is the, let us say 80% nickel. So, 80% nickel will be there with copper and they will be all in solution. So, here since it is a liquid, we call it liquid solution. Similarly, if I go to B, then in case of B, I will have the appearance of first solid, and that solid will be decided by a kind of parallel line with respect to composition axis. So, this will be the solid that will be forming, and other rest of the thing will be liquid. So, here we will have liquid plus solid, okay. And whenever I am drawing this, I am putting these points, this particular information, that means they are all under stable conditions. So, here we will see solid which will be nickel rich, and liquid which has the same composition as 80% nickel. And here solid is also a solid solution, remember that. So, how this happens, how this transformation happens, one solid comes out with a richer in nickel. So, those things will be talked as we understand that how to draw this diagram as a function of free energy composition diagram. So, free energy composition diagram, definitely you could see that we have to understand solution thermodynamics as well as we have to understand the free energy part and its association with the composition as well as temperature, of course, because pressure is always constant. Now, as we go to C, I could see that this is the line, I can draw a line. So, I could see that when we reach to C point, I will get liquid as well as solid, and here I will see the solid would be nearly 80% nickel, but liquid would be rich in copper. Now, D point if we see, it will be all solid solution. Here I am talking about solid solution as well as liquid solution, because I see that in between 100% nickel and copper, everything is mixed up, and everything how to decide those particular compositions by looking at percentage of nickel or percentage of copper in those phases. Okay. So, solid it will be all 80% nickel. Like that way all those phases are appearing, and I could see an in between. If I look at in between what happens, I will see that this composition and this composition, in between the red line, I have what are the phases? I have a rich solid which is nickel rich and copper rich. Okay. And we can also find out the relative fraction of those phases, the solid nickel rich and liquid copper rich. In fact, all throughout that vertical line A to D, we can determine what will be the fraction of different phases. So, that is also a beauty of phase diagram. So, I can understand phase transformation, I can understand fraction of different phases, as well as I can understand which will be a nickel rich, which will be copper rich. That means, if we consider binary phase, what in a particular phase on the way during phase transformation, I can determine the composition of those phases. So, that means, I can actually decide where to end, so that I can get that particular composition to be there in my hand to design some components or some engineering applications, the materials for engineering applications. So, that means, here also I could see that I am checking the stability of different phases, and here everything would be solution, either liquid solution or solute solution. I can see the coexistence of different phases, as well as I can check the fraction of different phases present in a particular system variable conditions. Okay. So, these will be all taken up as we go ahead. How to calculate the fraction? These will be decided by the lever rule, and we will understand that how the lever rule is applied, and what is the basic principle behind lever rule, and this is basically, we will see later on that this is basically nothing but the mass balance, and accordingly we will decide what will be the fractions of those phases. So, like that way we could see by giving an example of single component as well as binary system, and here I have put a copper nickel system where I could see that melting point of copper and melting point of nickel are placed at 100% of each of those components, and so melting point of copper is lower than melting point of nickel, that is what the copper is placed at the lower point, and we could also see different equilibrium lines, liquidus and solidus, and as I have seen in case of single component, on the line we could see that the two phases are coexisting, and beyond that line, for example, A to B, if it does not touch B, I could see that single phase is existing, and C to D, if I do not touch C, I could get all solid, but in between B and C, I could get two phase mixtures. Okay. So, like that way all the informations can be collected, and these information will be very vital when we try to design a kind of alloy systems for our application purpose. We will see the applications also later on. Okay. So, now let me just conclude in this particular, whatever we have talked about in this particular lecture is basically we try to define phase diagram. Okay. And while defining phase diagram, we also see what it means by stability of a phase, what it means by the coexistence of different phases, what it means when we try to look at the phase transformation in a system, and the importance of variables. So, let me stop here. We will continue our discussion in our future lectures. Thank you.